All right, let's dive right in. Today, we're talking about a key concept in trigonometry, amplitude. You can think of it like the volume knob for a wave. It's what controls its height. And trust me, by the end of this, you're going to have this concept down cold. It's a great question. You see it everywhere, from the ocean to sound waves. Why are some waves massive, powerful giants, while others are just tiny little ripples? Well, it turns out it all boils down to one simple but super powerful number. Let's get into it. So let's start with our home base, the standard sine wave, y equals sine of x. This is the classic. It's got this perfect, predictable rhythm, right? It goes up to a peak of 1 and then down to a valley of -1 over and over again. But that's kind of boring, isn't it? What if we want to mess with that height? What if we want to amplify it or maybe quiet it down? Well, this is where the magic happens. We introduce a multiplier, this coefficient we call a. This little letter is our control knob. It gives us all the power. So this a is what controls the amplitude. Now, the official definition is that it's the maximum distance from the wave's center line, or its equilibrium position. And the formula, it's super simple. The amplitude is just the absolute value of a. Now, pay close attention to those absolute value bars. They are absolutely crucial, and you'll see why in just a minute. Okay, enough talk. Let's see this thing in action. What happens if we crank that a all the way up to 3? Let's watch how our nice, normal sine wave transforms. And boom, look at that. The wave is now 3 times taller. It's peaking up at 3 and dipping all the way down to -3. We call this a vertical stretch. So the rule of thumb is simple. If the absolute value of a is bigger than 1, your wave is going to get taller. Okay, so that's how we make waves bigger. But what if we want to make them smaller? Let's dial a back down to a number between 0 and 1. How about a half? And just like that, our wave gets squished. It's vertically compressed. Now it only goes up to 0.5 and down to -0.5. So here's our second rule. When the absolute value of a is between 0 and 1, the wave gets shorter. So we've stretched it, we've squished it, but what on earth happens if a is negative? Does that mean you can have a negative height? How does that even work? Well, not exactly. A negative a does something really cool. It flips the entire wave upside down. It reflects it right over the x-axis. So instead of going up first, it goes down. But notice, the amplitude is still positive. The absolute value of -2 is still 2. The height is the same, just the direction is flipped. So let's just quickly recap our 3 big rules. If the absolute value of a is greater than 1, you get a vertical stretch. If it's between 0 and 1, you get a compression. And if a itself is negative, you get a reflection. That's it. Those are the 3 fundamental transformations you can do with amplitude. Okay, now that we've got the theory down, let's make sure it sticks by running through a couple of quick examples. First one up, y equals 5 cosine x. Okay, this is pretty straightforward, right? Our a is 5. The absolute value of 5 is, well, 5. So the amplitude is 5. That means the wave goes all the way up to 5 and down to -5. Easy. All right, now for one that's a little trickier. Y equals -3 sine x. This one's kind of a two-parter. First, the amplitude. We take the absolute value of -3, which is a +3. But we can't forget that negative sign. That tells us the whole graph is reflected, so from the starting point, the wave heads down first. Okay, I want to pause here for a second and talk about the single biggest, most common mistake people make with amplitude. If you can get this one thing right, you'll be golden. You need to burn this into your brain. Amplitude is always positive. Always. Why? Because it's measuring a distance, not a direction. You can't be -5 feet tall, right? Same idea. Amplitude tells you how far the wave goes from the middle, not which way it goes first. So let's look at this side by side. On the left is the trap people fall into. They say y equals -3 sine of x and say the amplitude is -3. That's wrong. The right way to think about it is this. The amplitude is the absolute value of -3, which is 3. That negative sign just tells you about the reflection. So who cares? Why does any of this matter outside of a math class? Well, it turns out this is stuff that shapes our actual world. Let's talk about the oceans for a second. Believe it or not, the rising and falling of ocean tides follow a beautiful sinusoidal pattern. And for people like marine engineers, calculating the amplitude of those tides is mission critical. They use a simple formula that's doing the exact same thing we are, finding half the distance between the highest point and the lowest point.
So for instance, let's say high tide in a harbor is 6 feet above normal sea level, and low tide is 2 feet below. We just plug those numbers right into the formula. That's 6 minus -2, all divided by 2.
And that gives us a tidal amplitude of 4 feet. Now, that number might not sound like a lot, but in the real world, it has massive, massive consequences. So why does that 4-foot number matter so much? Well, engineers use it to figure out how high to build docks so ships can load and unload. It helps them know if shipping lanes are deep enough for giant container ships. And it's absolutely vital for building seawalls that are strong enough to protect our coastal cities. So you see, what starts as a simple number in a trig equation turns into critical information for building our infrastructure. Amplitude isn't just abstract math. It's a tool we use to literally shape and navigate our world. So we've totally mastered changing a wave's height. We can make it taller or shorter. But what about its speed? How do we stretch or compress a wave from side to side? Well, that's a fantastic question for our next explainer. Thanks for watching.